Good morning, everyone. Welcome back. Before class begins, I'm going to do a quick overview of Assignment 3. And before I even do that, I quickly wanted to note that the Quiz 2 regrading requests folder was not visible on Friday, but that's fixed now. So if you found a potential grading error over the weekend, you can send that to me now. So with this assignment, we're finally getting into coding assignments. This is sort of going to be a review of the idea that ADTs are like the idea behind a data structure, and the data structure is the actual implementation of the ADT. You'll be given a application-specific ADT, similar to the Comp 2140 example from class, and you'll have to implement it twice. The marker, like from the perspective of the marker or someone else using your code, they would have no idea which implementation they're using, but you'll know that one of them uses a sorted linked list, one of them has a hash table, one of them might be more efficient than the other, who knows? And then this assignment also has a written question that's sort of unique for this course. It's not a proof per se, but it is still pretty technical, mathy. The submission for this is more like assignment 1. There will be a mix of CrowdMark submissions and UMLearn submissions. This time mostly UMLearn, but you can still get a bonus mark for doing the written question at the end digitally. New rule now that we're actually talking about coding data structures, you need to make them yourself. So anything built into Java like linked list, stack, queue, array list, you can't use that. However, there can be exceptions to this. The philosophy is that if a question isn't really about a certain data structure, then you can just use Java's implementation of this. So if there's an instance where you think you could make your life easier without removing too much educational value by using a built-in data structure for a specific part of the assignment, ask me. I'll probably make an exception. The coding question is all in a made-up scenario about developing a fishing game where you're tasked with making the part of the game's code that keeps track of the user's fish. There's a specific folder setup and fish class you need to make. This isn't worth marks, but it'll kind of be necessary for everything else that's worth marks. So do it carefully. This lexicographical order idea, you could ask me for clarification, especially on the discussion forum so others see it, if you need any clarification, but the intuition should be pretty easy. Lexicographical order is basically alphabetical order, but with it being slightly generalized to account for things like numbers, spaces, and symbols. We're also going to use interfaces for the first time. As long as you follow these instructions, it should be pretty basic. And then the bulk of this assignment is implementing that ADT twice. You'll do it first with a sorted linked list, and again with a hash table. This is so far all stuff that we've covered before. But the hash table implementation uses some stuff that you don't know quite yet. You might know it if you were reading ahead. But it'll be stuff that we'll talk about this class, or maybe next class if this ends up or if the assignment overview ends up taking too much time away from that. In particular, if we get through today's lecture fully, you'll know what polynomial hashed function with Horner's method means, as well as managing collisions by separate chaining. I'm not going to go over the interface or the specification of the ADT because, I would just end up reading from the assignment, and today's lecture has a lot in it, and I want to do my best to get through the whole thing so that you all know everything you need to know to do the assignment. I wanted to do another quick demonstration of using the command line because this uses a special flag to enable functionality for the tests that you need to run. This is definitely possible to enable inside of other IDEs, maybe even editors like VS Code. But that's not my expertise whatsoever. If you want to use something other than the command line, you'll have to figure out how to replicate this. Yeah.
For inventory ADT, are we assuming that it has a finite size, or it's like just an infinite amount of inventory spots?
You'll be assuming that it's infinite. The linked list, by the way that it lets you lets you allocate memory dynamically, gives you functionally infinite space anyway. And then you might think that the hash table would have finite space based on what you know. A completely valid assumption to make, considering that all you guys know right now is that they're made using arrays. But it turns out we'll be using a way to allocate memory dynamically for the hash table too. So both these data structures will be able to use unbounded space. So when you're in the terminal, Mac users can type cd for change directory and drag the directory you want to navigate into the terminal. Windows and Linux users could almost certainly do something similar. Going to do ls for list, and then cd again, change directory, to go into one of the subfolders. And then the process for running the code is very similar to the assignment 1, just with that additional -EA you need to worry about. That stands for enable assertions and is necessary for the test suite that I gave you to work. Previously, I told you about using 2 separate commands, javac and java, but there's a nice way that you can chain together commands, and it's probably going to show up in the autocomplete as soon as I start typing. Yeah. Between 2 commands, you can write 2 ampersands and to chain them together into one command. So this command will execute javac testinventory.java and also java-ea testinventory g. And then it works. It also meows. If you forget to enable assertions, it'll ask you nicely to do so. So your output should look like this. Meowing is optional. The marker will be making sure that the output looks good. It doesn't have to look exactly like mine, but it should print the fields of the object. And then question 3 works identically. You might run into trouble if you're using tools other than the command line. If, oh, by the way, I'm using cd 2 periods to change into the directory that contains this one. A lot of tools will get very confused about the fact that you have multiple files called inventory.java and fish.java and testinventory.java. Like, which one's the real fish? It gets scared. So this is a known issue with the assignment. It's a natural consequence of implementing the same ADT twice. If you're getting compiler errors that have something to do with duplicate classes, just don't open the entire assignment directory in your IDE at once. Separately open A3Q2 and A3Q3. And if you open just those folders, then your IDE won't know about the other fish inventory and test inventory files that exist elsewhere. And finally, the written question. This one is kind of the most practical question ever, actually. This sort of analysis is very common on the job. Like, you'll never have to actually write out these responses for marks, but it is a very realistic situation to be thrown into a new code base, and maybe your boss or an older coworker gives you a quick explanation of this, but then as you're coding, it's up to you to figure out things like, how should I configure this to minimize the likelihood of incorrect estimates? What is this even supposed to do? Questions like that. This probably looks extremely intimidating, but don't worry. You don't have to do any proofs to fill out this table. This is also a sort of demonstration of how you might reason about data structures in the real world. You are free and encouraged to do all this completely based on vibes. In fact, I don't think it's possible to do it rigorously because I don't supply you with any specific algorithms that you could use to make cost functions. You just have to reason about things like, oh, this does one thing for every item in the list, so it's probably linear time. This does stuff that's independent of the number of items in the list, so it's probably constant time. That sort of thing. Lastly, I want to do a clarification, or I want to give a hint to everyone. To completely clarify this would kind of give away the question, but Part E talks about minimizing the likelihood of incorrect estimates, and Part F talks about increasing the accuracy of estimates. These two things kind of sound like the same thing, but they're not, and it'll be up to you to explain how they're different. And I'm going to just put you on the right path. I'll put you on the right path by showing an example of minimized likelihood of incorrect estimates and accurate estimates. The difference will hopefully become pretty clear, but it'll still be up to you to explain it. Now we're back to hash tables. We learned about hash tables last week and how they work. Notably, the notion of having a hash function that maps keys to array indices. So we can then use the fact that arrays let you index to any arbitrary index and get that data item in a constant amount of time. to access values to do with keys of any types in a constant amount of time. Two parts to a hash function. The hash code takes non-integer keys and converts them into integers, and then the compression map maps the hash code into a range of valid array indices. Last class, we talked about compression maps to map things like 4-digit library index numbers to 3-digit array indices. And we're going to talk about hash codes today. Ideally, good hash functions are fast to compute and they minimize collisions. So it's impossible to make it so hash function results are always unique. It's often an intrinsic thing of the data you're storing that you just have less space than there is possible values for the data, and that makes collisions inevitable by the pigeonhole principle. But this should happen as seldom as possible. So let's talk about hash codes. We found that the simplest hash function is just taking an int and then returning that int, the identity function. That was technically a hash code. The second simplest hash code is if a key is not an integer, but is the same size as an integer in memory. You'll learn about that in more detail in other courses, but basically all of Java's primitive types, so int, string, float, bool even, take up roughly the same amount of memory as an integer. So you could just cast the primitive value to an integer and use the result as a hash code. So this simple hash code for a key that is a char can look like this one-liner on the screen. Just cast the key into an int and it'll just work. I think in practice it'll map chars into high double-digit numbers, like in the 60s to 90s. Whatever integers you get out of this process is fine. The important part is that it casts every character into a different integer. And then if you have less space in your array than you have possible values, then your compression map will turn them into valid array indices. But now it's going to get complicated because the most common key type, I bet, don't have stats, but this is intuition. Most common key type is probably string. And strings, as collections of characters, take up way more memory than a single char. So we'll need to have some creativity to make it so strings can be turned into numbers, integers. We're going to do this in terms of the characters in the string. So each character we'll turn into an int, like described earlier, and then do some sort of operation on the ints to get a single integer. The first idea is that you could add up all the integers to get the hash code. So if you want to hash the key cat, you'd cast C, A, and T into integers. We're using a simpler mapping than Java would use in practice, where each letter just gets casted to its position in the alphabet. But like I said earlier, the exact mapping doesn't really matter, only the fact that it is a mapping. So you cast each character to an integer, add those integers together, and then that could be your hash code. That's good, maybe, simple to understand. But any strings that consist of the same characters will get the same hash code patterns. or will get the same hash code. Patterns in the keys give rise to patterns in the indices, and we're trying to avoid that. So there's another thing we can do that can make it so strings with the same letters, pretty sure they're called anagrams, get different hash codes. So we're using cat as an example because it's a 3-letter word, easy to understand, also very adorable. And the problem here is that a similar word like act would get the same hash code. And this idea, polynomial hashing, or polynomial hash function on the assignment, it prevents this by sort of assigning more importance to letters that are earlier in the string. So the key cat, it makes it so C has more of an effect on the hash code than T, and thus the ordering makes it so words like cat and act don't get the same hash code. The order of the letters within the string, I mean. So what are we actually doing? So we're going to start with a small prime number. Why is it a prime number? Why are prime numbers going to keep showing up in this course? I'll talk more about it later. It has to do with divisibility rules. So let A be a small prime number. 13 is a good choice. Convert each character to an integer like before, and then calculate this whole thing. Ooh. You can imagine this generalized to more letters, but we'll have earlier letters multiplied by a to the power of relatively large number. The second letter multiplied by a to the power of a slightly smaller letter, all down to the last letter multiplied by 1. And then once you have all those numbers or all those letters turned into integers that are then made larger based on their position in the word, you add all those up and you get your hash code. And as discussed before, the key act would get you the same hash code as cat if you just summed up the integers. But now that we've started using this method, it gets you a completely different result. And that's because you're multiplying the numbers associated with these characters by totally different powers of that prime number based on where they are in the string. This is called the polynomial hash code, and using that number 13 results in a uniform distribution of hash codes when applied to English words. So even though there are plenty of patterns in English words, like some letters being more common than another, words being based on other words, using this lets you get a totally uniform distribution of hash codes. Every single potential array index is just as likely to appear as any other. So this is great in theory. We have achieved our goal of avoiding collisions as well as we can, under the assumption that we have infinite memory and also infinite time. But we don't. We're going to have to make some adjustments so that this can work well on actual computers that are limited in the size and the time, limited in the memory and the time that they have. More specifically, the results can be really large. So you could imagine hashing a really long word. Like say a word has 10 letters in it, and then you have to raise 13 to the power of 10 and also 9 and 8. Yikes. That will probably actually overflow an int, which can lead to pretty unpredictable behavior. And also, even worse, implementation-specific behavior. Not just implementation-specific as in the code that you're writing, but implementation-specific as in the specifications of the processor of the computer you're running on. Again, this will be covered more in other courses, but dealing with overflows can get really nasty because they can work differently on different processors. You want to at least make it work consistently across computers. The other problem is that we want our hash function to be fast to compute, but calculating all these exponents can be time consuming. Case in point, say you're calculating the polynomial hash code and you're calculating all these powers of A by repeated multiplication. It's the most sensible way to calculate exponents that you might think of, or the first that you might think of. So to calculate A to the M, you just multiply A by itself, presumably M times. I guess this is slightly generalized. Each of these M, M-1, and so on are referred to as AJ, so we multiply A by itself J times. How many operations do we need to do this? Well, we can see from the earlier slide that each of these AJ requires J multiplications to do. And then there are going to be 1, 2, so on. There are going to be M such terms because the definition of the polynomial hash code starts with the power of M, counts down by 1 until you get to 0. So you're going to do something J times M times, where J is based on M. Kind of just word salad verbally, but this summation expresses it quite nicely. So it takes J-1 steps to do this whole loop. And then to do the complete polynomial hash code, you have to do that M times. Using the summation identities we learned about earlier, this turns out to take O of M squared times. And also remember that the variable M is defined by the length of the word that you're hashing. And then the variable J is the summation variable. It is the index of the character that we're currently working. So we need to do an amount of multiplications that is in big O of M squared. And then you also need to do M multiplications and M additions. This is because there are M of these terms, and for each of them you'd need to multiply A to the M by the mth character. So for each of the M terms, that's one multiplication and one addition. Oh yeah, I didn't explain, the addition is just to add the terms together. So that would make it something like m squared plus 2m. But because of how asymptotic notation works, m squared plus 2m is in big O of m squared. So we just say the same, that the whole thing is in big O of m squared. When using asymptotic notation practically, we always want to simplify it to like the simplest possible function inside of the big O. In this case, saying that this hash code is in big O of m squared plus 2m wouldn't really tell us any valuable information that isn't conveyed through big O of m squared. We can do this better. To make things a bit easier on us, we're going to assume each key is a string of length 5. The math we're going to do works on strings of any length, but you already have heard how clunky it is for me to talk about like an m character string and like the mth character in that string and stuff like that. We're just going to use a specific number. So K is a 5-letter word with characters C4, C3, C2, C1, and C0. And we're doing the polynomial hash code of that. It's going to look like this. And we can notice that all of these terms, except the last, have an A term in them, at least A to the power of at least 1. So we can just factor that out and get something like this. So you have a bunch of terms multiplied by A plus C0. And then within these brackets, notice that all but one of these terms have a term with a power of A that is at least 1. So we can factor that out. And we can factor that out. We just keep factoring until we have this expression that looks like a bunch of nested brackets with an A multiplying each set of brackets. It may or may not look like this at this point, but it turns out evaluating this instead of this gives you very real time savings in terms of the number of multiplication operations you need to do. To evaluate it, you would do multiplication and an addition, multiply that whole thing by A, and then you'll be left with brackets, and you just repeat that until you have a sum. So now, instead of going through each term and doing a repeated multiplication, along with another multiplication and an addition, you now have a bunch of sets of brackets such that for each one you do, one multiplication, one addition, and then one more multiplication. So 3 operations. And you do that m times. In this case, m equals 5. So I think, personally, 3 operations per term is way better than j or m or some variable number of operations per term. The fact that you're doing a constant number of multiplications and additions per term instead of an amount of multiplications and additions per term that depends on the length of the string sort of removes a multiplicative term from the asymptotic time complexity, making it so the overall calculation requires O of m operations instead of O of m squared. And as you know from the theory earlier in this course, like the difference between 2m and m isn't significant. The difference between m squared and m squared plus 2m or whatever isn't significant. But a difference that changes an exponent in a variable is significant. And this different algebra will run meaningfully faster than what we were doing before. This thing's called Horner's method, and this exercise for the reader is strongly recommended because it is just the hash table implementation in the assignment. So I think that's pretty cool. We found a way that smarter organization of our code, just doing a bunch of factoring out when thinking about what code we're going to run, results in meaningfully faster code. That solves one of the issues that we mentioned earlier, that the hash code is slow, but there's still an issue that it might return very large numbers. We can solve this by taking advantage of properties of modulo operation. Basically, it has a kind of sort of distributive property to it. The expressions on the left and right side aren't equal. They won't be the exact same number most of the time, but they'll be equivalent modulo n, which means that they have the same remainder when divided by n. Which means that if you have two numbers that are equivalent modulo n, you could take the modulo n again to get identical answers. So you can use these properties to greatly simplify certain operations. Like say you wanted to calculate this, 343 times 517 modulo 10. This might show up when you're implementing Horner's method, where like 343 is one of those powers of A, 517 is one. Actually, I don't think this exact operation would appear, but you still get the idea of how this is an operation that you might want to simplify, seeing as Horner's method involves lots of addition and multiplication of large numbers. So you can do this the hard way of just calculating that product and then applying the modulo operation. But using this property, we can kind of sort of distribute that modulo 10 over the numbers. So I'm just going to write that this is equivalent to 343 mod 10 times 517 mod 10. Doing this distributive trick lets you turn this into a series of much easier operations. 343 turns into 3, because that's a remainder of that divided by 10. Likewise, 517 turns into 7. And then much easier than calculating 343 times 517, is calculating 7 times 3. We all know 7 times 3. From that, we get a number that is equivalent modulo n. In this case, has the same remainder as the actual result when divided by 10. So we can just take the modulo again to get that remainder and get a number that is equal to that result. More practically, if we want to keep our answers to a manageable size while using Horner's method, we just do a modulo n after each step in the calculation. So like in each of these R calculations, yeah, we just apply modulo n after each of those steps. Yeah.
For applying our cost function analysis to this, would the easy way be 4 steps, while the hard way is only 2 steps?
Ooh. Oh, probably. Let's see. Okay, so this could totally turn into an hour-long rant about computer architecture, but I'll try and keep it brief but still informative. Assuming that any two numbers take the exact same amount of time to multiply, then yes, this will be faster than this. But that might not be the case. The actual multiplication algorithms that are embedded into your CPUs may or may not take longer to calculate products with large numbers. So the practical question of whether the hard way is faster than the easy way is a huge it depends. It might be different for every single computer in this room. Additionally, under that assumption that all numbers take the same amount of time to multiply, the hard way becomes easy for computers, and then the easy way becomes easy for humans. So instead of hard and easy, we have better for humans and better for computers. And both of those have a place. Last thing I wanted to mention was that our main motivation for keeping the numbers small is overflow. Aha. The danger of overflow, like when a number becomes too large and just wraps around into a smaller one, presents even more of a processor-specific danger, and it's something that we definitely want to avoid. So, I think more meaningfully than my discussion on time complexity for the easy way and the hard way, the easy way becomes something of avoiding overflow rather than trying to make it faster. And it's a perfectly acceptable compromise if it becomes slower in the pursuit of avoiding overflow. Cool. Okay, half an hour left. I think we might be able to do this. I'll go over the assignment 2 solution in class eventually, by the way. I just want to get through this as quickly as possible so that you have everything you need to do assignment 3. So, the polynomial hash code we just learned about works to reduce collisions, but unless you have an array in your hash table that can store every single possible word, you probably don't because there are infinitely many in theory, you're going to have collisions eventually where multiple keys hash to the same array index. So even though the first step is and should be how to make collisions not happen as much as possible, we do have to eventually worry about what we're going to do when there is a collision. Oh, great. Actually, there's one more thing I need to talk about with reducing collisions before I can actually get into dealing with collisions, which is a great shame because I think that dealing with collisions is much more interesting than reducing them. We need to remember something about the modulo operation, and that if we're doing something like k modulo n, very practical because k is usually a key and n is usually an array size. If k and n share a common factor, then those two, or then any other keys that have that common factor will map to the same array index. And that actually goes into why we're using prime numbers for this. I feel like there's a better explanation for that somewhere. Although, if I don't get around to explaining it well, we could just go with, yeah, use a prime number for your array size. Don't think about it. Oh yeah, basically every key that shares a specific common factor with n will hash to the same index in n. And that's real bad. Like, I think we had an example earlier with like a 200 size array and keys that ended with either 0 or 5. In those cases, they all had the common factors of 5 or 10 with the array size, and then they ended up all going into the same couple array indices. I feel like I'm not giving a very good explanation for this. The good explanation is about, or it involves a bunch of number theory and divisibility stuff that I'm not as familiar with as I should be. So if anyone wants a deeper explanation, we could talk about it during office hours while I have access to Google, and then I could find a Stack Overflow thing and then explain it to you. But for now, we're just going to remember to use arrays whose length is prime. This will prevent situations where the key shares common factors with the array length and the collisions that result from that. Anyway, the first strategy for dealing with collisions when they arise is called open addressing. So say you want to insert an entry with key k into the array, calculate h of k, and then check index h of k in the array. If that position in the array isn't occupied, just insert the entry there. Cool. If the position is already occupied, then we would have a collision. Then we would search, or we can also call this probing, the positions following it in some predetermined pattern and insert the entry in the first available position. So like if you have an array, and say like indices 1, 2, and 4 are already occupied, and then you're trying to insert an item with h of k equal to 2, you would check Index 2, see that it's occupied, move on. Index 3 is free, so you put it there. And then, say you're inserting another item that also happens to hash to 2. You check 2, it's occupied. Check 3, it's occupied. Check 4, it's occupied. And then move on to 5. So, hopefully, you're already seeing that this could get very inefficient when we have when we have a lot of collisions. Like, say we have a really bad hash function that tends to produce the hash value 2 extremely often, we would just have a huge clump of values from 2 up to the number of elements that hashed to 2. And then attempting to insert or search for that item basically just becomes linear search. So again, this can get very, very bad when there are lots of collisions. So that's why you want to try to reduce the amount of collisions that occur. But then collisions are inevitable and you have to manage them somehow, and this might be good enough if you've already put work into making it so collisions don't happen too often. The pattern of going to indices sequentially is what I demonstrated. So like 2 is occupied, check 3, and then 4, and then 5. But there's another one you could do. Let's see. And that's to have a step amount that is like, that is a specific number. And that step size should be relatively prime to the array size in order to make sure that you can actually hit all of the array indices while doing the probing. So you might have noticed I erased index 6. The array now has 6 elements because we started at 0. And say I made the step amount 2. So if 2 is occupied, then we would go 2 over, check 4, and then 2 over, which would wrap around to 0. And if that were occupied, we would go back to 2, and then keep circling through the array, only checking even indices, completely missing indices 1, 3, and 5. And that happens because I chose a step size that has common factors with the array size, 6. So if you're implementing this, make sure to choose a step size that is relatively prime to n, meaning doesn't have any common factors with n. So 6 is tough to work with because it's a highly composite number. Can't think of a step size that's relatively prime to n. But if I just reintroduce index 7, then since 7 is a prime number, no other numbers have common factors with 7. So everything is relatively prime to 7. And thus, our strategy of using a step size of 2 will will let us access those odd indices. It's weird. It's number theory. I don't like number theory. Keep your numbers out of my math. This example might be what I just yapped about, so I'll probably make it quick. Say you're making a table of reference books and your hash map is to map the first letter of the author's last name to an integer. Bad hash map, but don't worry about it. And suppose you insert the following names in that order: Alfors, Auden, Cushman, and then Breton. Alfors will hash to 0. The table will be empty at that index, so it's just put there. Auden also hashes to 0, but that index will already be occupied at that point. So you put it in index 1 instead. Cushman gets indexed 2 naturally, and then Breton, which should be at 1, has to go over to 3 before it finds a space for it. Now suppose you search for Breton. I briefly mentioned that when inserting Breton, we need to move along a few spaces. And the same happens when you're searching, not just inserting. Your hash map gives you an index of 1. You check that the name is what you're looking for. In this case, it's not. So you step through the array until you find either the thing you're looking for or an empty space. So in this case, the search required 3 probes. I already mentioned also that if you're looking for a value that isn't in the hash table, your search would go until it finds an empty index. So if you're looking for Anderson, that would hash to 0 because it starts with A. And then you would keep checking every index until you get to an empty one. The fact that index 4 is empty means that Anderson was never added to the array. Otherwise, there would be Anderson in that index. So the search fails. You returned false or something. If the entire array is completely filled up, then the search would continue until you've reached the end of the array. And like I said, this can get pretty bad. We use a term called the load factor, which is kind of like the percentage, or more accurately, proportion of array indices that are filled up. And by some empirical research, like literally just experimenting or running experiments and making a graph, computer scientists have found that this strategy is acceptable for tables with low load factors. But if you have a load factor of 0.75 or more, so 3/4 of your array indices are filled, then this will perform very badly. In the worst case, searching requires O of n time because you're basically just doing linear search. You have to iterate through all or almost all of the entries in the table in order to find what you're looking for. Completely ruins the point of the hash table. So I'll say it again. Collisions are inevitable, but you can and should put work into reducing collisions as much as possible before implementing a way to deal with the collisions that do happen. And then, hopefully, you end up with relatively few collisions and a low load factor, and this can work. However, I think this one's totally better. An alternative to the strategy we just looked at, which, by the way, is called open addressing with linear probing. You won't be tested on that, don't An alternative to that is to make each entry the top node in a linked list. And then if you have a collision, like two entries are hashed to the same index, you just insert the new entry into the corresponding linked list. Each linked list is unsorted, so you can always perform that insert process in constant time, even if there's a collision. So, as a consequence, insertion will always be constant time. We found that with open addressing, insert could take a long time if there are collisions and lots of filled up spaces. But with this strategy, it's always constant time. And then how does search perform? Still pretty badly in the worst case, but it's not as severe as open addressing. We'll go through that soon. And also, this strategy is kind of what I talked about in the beginning of the class, in that this lets you allocate memory dynamically for a hash table. You should still choose an array size smartly for the sake of avoiding collisions. But then once you start adding stuff to it, you just allocate memory for more linked list nodes. And then, in theory, you can store an unlimited amount of items. So this is the same example as before, but using separate chaining now. If you want to search for Anderson, you first go to as described, or just like earlier. Again, Anderson starts with A. We're using a crappy little hash code that uses the first letter of the author's last name. So you go to index 0, and then search the corresponding linked list until you either find what you're looking for or reach the end of the list. This technically has the same worst case as open addressing, but it's so rare that I just say that the worst case isn't as bad. Technically, you could have a hash function that is so terrible that it hashes every single possible key to the same index. And in that case, your hash table just becomes a single linked list that is stored inside of an array that's wasting a bunch of space. And then this would perform identically to a linked list, unsorted linked list specifically. Everything takes linear time, no good. But in practice, if you do a even slightly okay, even bare minimum job of choosing your hash function, then you'll get different items, like different keys hashing to different array indices. And then the worst case for searching for an item is proportional to the number of keys that hash to that index. In this case, the number of authors that share a last name. Like in this example, searching for the author with last name starting with B was slow because we would go to the second index and then have to search until we find it. Here it's a lot better. Braden's right there. These linked lists are sometimes referred to as buckets. You're categorizing values into buckets based on some property as defined by your hash function. In this case, first letter of last name. And finally, something that is not a strategy for reducing collisions or dealing with them is just making the table bigger. You should use a decently large array in order to have space for lots of different hash values, but you can't just avoid collisions by making the table bigger. So say that you know you're going to put 1,000 items into your hash table, and that you have a good hash function, and then you choose a really big array size, like 4,000, will that make collisions unlikely? Well, in general, the probability of having no collisions is like 1 for the first item that you're inserting, and then progressively smaller fractions for successive items. Like there's a 100% chance the first item will not be a collision, a 3,999 out of 400 chance that the second item will not have a collision, 3,998 over 4,000 chance that the third item will not have a collision, and so on. And in general, we get this expression for the likelihood that there will be no collisions after inserting j items. And to make that more specific, turns out the probability of having no collisions drops below 0.5 when j equals 75. So you're adding 1,000 entries to the linked list, 1,000 items to the hash table, and you've gone through less than 10% of those items, and you already have a 50-50 chance of having a collision in there somewhere. So even with a humongous table, you'll have an extremely low probability of not having any collisions. So like after all 1,000 entries have been added to that 4,000 item hash table, get a 10 to the negative 45 chance of having no collisions. Whew. So you can't make the table big enough to prevent collisions. You'll have to use one of the collision resolution methods, even if, and like even after, because you'll totally be doing this. What was I saying? Even after choosing a hash function smartly to make collisions as rare as possible. So that's the end. Do I want to talk about the next thing for 3 minutes? Yeah. Oh, yes. That's actually way better than me doing the first fragment of the next lecture. What's up?
Just to confirm, the probability of having no collisions drops below 0.5 when j equals 75, no matter the array size you get?
I think
Or
this.
is it like any specific example?
Yeah, I think this is specific to this example of having 1,000 items with an array size of 4,000 indices.
So how do you determine when the probability of having no collisions drops below 0.5 for any other size, or is that something you don't want to know?
You don't need to know this for this course, but you can definitely generalize this formula for array sizes other than 4,000 to get a formula for the probability of a collision, the probability of no collisions with other array sizes. Cool. That brings us slightly closer to the end of class. I'm not going to do anything else. I'll see you all tomorrow.